Good afternoon or good morning from the U.S. Fish and Wildlife Services National Conservation Training Center in Shepherdstown, West Virginia. My name is Ashley Fortune, and I would like to welcome you to today's broadcast of the NCC-WSC's Climate Change Science and Management webinar series. This series is held in partnership with the U.S. Geological Survey's National Climate Change and Wildlife Science Center. Today's webinar will focus on the topic of fish habitat and climate change, implications for the desert Southwest, Midwestern smallmouth bass, and Eastern Brook trout. Our speakers today are Craig Pauckert, Tyrell DeWeber, and Joanna Whittier. Dr. Sean Carter, Senior Scientist at the USGS National Climate Change and Wildlife Science Center in Western Virginia, will now introduce our speaker. Sean, welcome.
Great. Thank you, Ashley. Great, thanks. Well, thank you, everyone, for joining us for our webinar today. It's my pleasure to introduce a talk on managing the nation's fish habitat and multiple spatial scales in a rapidly changing climate. And my understanding is this is going to be a joint effort. And so I'm happy that we have Joanna Whittier, who's a research assistant professor in the Fisheries and Wildlife Department at the University of Missouri. Her research focuses on factors leading to declines in species populations. We also have Tyrell DeWeber, a PhD candidate at the Pennsylvania Cooperative Fisheries and Wildlife Research Unit at Penn State. He's currently investigating climate and land use change implications for river habitat and brook trout. And then last but not least, Craig Pauckert, who's the leader of the Missouri Cooperative Fish and Wildlife Research Unit and also associate professor at the University of Missouri. And his research focuses on conservation and management of river and stream fishes and the effects of climate change on aquatic systems. So welcome all of you, and I'm happy to introduce you and look forward to your talk. So you have the floor.
Okay, thanks, Sean. Hey, this is Craig Pauckert over at the Missouri Co-op unit, and I'm going to start the talk today and spend about 15 minutes with some introduction and talking about smallmouth bass in the Midwest, and then we'll switch it over to Tyrell to talk about Eastern Brook trout and bring it back to Jody Whittier to talk about some work in the lower Colorado River Basin. But this is really the first part of a 2-month talk, two 1-hour talks, one today and one next month, on a pretty large project, as you can see from the PI list on the front of the slide there, that this is a big project that collectively had about 17 investigators on it and really was using a lot of existing data leveraged from all sorts of groups, in particular the National Fish Habitat Action Partnership, Aquatic Gap Analysis Program, also federal aid to support fish restoration, Park Service, and other funding sources as well. So it is a big project, and we're going to try to get through about half of it today, and then the other half in about a month. So I just showed you the list of the PIs, and they ranged from land use change modelers, climate change modelers, and fish folks. But these are the people that are really doing the work. We have quite a few postdocs, PhD students, research and academic staff, and these are the on-the-ground folks, several GIS and database type technicians helping out with the land use change modeling and just in general GIS work, because there's quite a bit of that on this project. You'll hear from Tyrell here in a little bit from Penn State to talk about a little bit of the Eastern Brook trout work. And I'm going to actually start it off talking a little bit about the introduction here. So this is a big project, and we're going at it from multiple directions and multiple different spatial scales, and also going at it from individual species all the way to fish communities. So the first phase of our project really is talking about fish populations, and in particular smallmouth bass growth and consumption in the Midwest. And that's what these 4 stars are in the native range of the smallmouth bass in the Midwest from Oklahoma all the way up to Minnesota. And then we're actually going to expand out and go to looking at distributional changes of a key species in the east, the Eastern Brook trout, in the Eastern Brook trout joint venture age. And Tyrell will talk about that. But then we're actually going to head west, and Jody today will wrap up a big part of our talk on looking at fish communities, native fish communities in the lower Colorado River Basin. And then next week we'll actually continue that fish community at a regional scale and looking at Midwestern stream fishes. And when I say Midwestern streams, that's going to be mainly Minnesota, Wisconsin, and Michigan. And then we're also going to look at cold water habitat in those Midwestern lakes as well. And then finally, we'll actually end with a national scale assessment led primarily by Michigan State, and looking at all or not all the streams, but the entire United States. And this is a more coarse scale assessment, and this is actually why we set it up this way. Is we knew at a national level we wouldn't be able to get the detail that we may have at these more regional levels or even the individual species or population levels. So some of this work that we were doing is almost a feasibility study to show what we can and can't do from a nationwide scale all the way down to regions based on the different data available in each of the regions. So as I mentioned, today we're really going to focus on smallmouth bass, brook trout, and then the lower Colorado River Basin, and then next month, May 9th, is the rest of the talk. So just in the interest of time, unfortunately, we're really not going to get into a lot of the details on the actual downscaled climate projections or the land use projections. But these were critical in our assessment, as you might imagine. These were the base for our assessments. We needed the downscaled climate projections so we could actually use this information to get hopefully temperature, stream temperature, and air temperature and precipitation that we can link to stream temperature and stream flows. And we needed the projected land use, and this was mainly agriculture and urban land use, to link that to our landscape level metrics, which we've been using quite a bit in these assessments that are used as surrogates for fish habitat. And these two critical pieces of information were input into the rest of our assessments that we're going to show you here in a couple minutes. One of the reasons why I'm not going to go into the details of land use and climate models is, one, they're already available, and two, they're published. So the climate models were done by Steve Hostetler and his team out at USGS in Oregon State. And on the screen now you can see the web link as well as the publications associated with the information that we're going to project here. We use 3 GCMs and at a spatial scale of 15 kilometers, so pretty fine scale resolution. And we also summarize this information by day, but really used a 5-year average. So when we talk about like 2060, that's the average over 5 years for a particular day around the year 2060. We had 66 total variables that we received from Steve for this assessment. But the most logical ones that you'll see are things like air temperature and precipitation, and those are really used in our models for how that affects fish habitat and fishes. Now, the land use change is kind of in a similar situation. Brian Pijanowski is part of our team at Purdue University, and he's got a nice website, the link is up here, that shows the land use change in urban and ag land use with in 10-year increments using the 2001 National Land Cover as the base map. And this was at the 30-kilometer scale. And for the urban land use, we projected out to 2100. For the agricultural land use, only to 2040. Brian wasn't very comfortable projecting agricultural land use out beyond that. Lots of variability and lots of uncertainty with the ag land use. But once again, this information is available, and there's the publication, the reference for the publication that just recently came out using this information. So unfortunately, that's really all I'm going to talk about with the climate and land use data. But as I mentioned, this was critical. So now what we needed to do is we needed to feed that information into our other assessments on fish and fish habitat. And the first one I'm going to talk about is at this individual scale. It's actually looking, doing some individual-based modeling, bioenergetics modeling, to look at how climate change affects growth and consumption of smallmouth bass in the central U.S. here, where it's actually native. So this isn't out like in Washington or the desert Southwest where it's a non-native and it's a problem, but it's actually generally considered a good thing in my neck of the woods here. And this was part of Allison Pease's postdoc work when she was with me here at the Missouri Co-op unit. So for this particular project, we really wanted to look at the individual and population level impacts of climate change. And as you'll see, if you're familiar with the climate change research and even some of the talks today, there's a lot of work on distributional changes in fishes, particularly recently on a lot of trout work in the Pacific Northwest in the western U.S. But we really wanted to kind of focus on the population level and the individual level to show that just because a fish is there, it doesn't necessarily mean that it's doing well. And we wanted to predict growth and consumption in these 4 populations of smallmouth bass. And these are across a strong latitudinal gradient from Minnesota, from the Mississippi River, Minnesota, down to a smaller river in Oklahoma, the Glover River. And we chose these 4 populations for a couple reasons. First is because of the latitudinal gradient, we really had a range in temperatures. But also, there was a fair amount of data available, both stream temperature data, air temperature data nearby, and then fish data at these locations from various studies. So the first thing we wanted to do with this particular study is at these locations, these 4 locations, to relate air temperature and stream temperature. And this is where it was really nice that we had temperature gauges nearby in these particular stream reaches. And we just used the last 5 years or so of data to compare air and stream temperature. And we found actually pretty good relationships just with that simple regression model. Depending on the site, the R-squares were 0.76 to 0.87. So we felt pretty comfortable that we could predict stream temperature from air temperature. And then, since we had that relationship, we're able to plug this into the downscale climate models with our air temperature data to predict in the future what the potential stream temperature would be at those particular sites. And we did this with the 3 GCMs, as I mentioned earlier. And just for the purposes of this talk and clarity, we're going to focus primarily on comparing present day to 2060. And when I say present day, it's a little misleading. It's actually, we used 1995 as present day for this particular study, and the main reason for that is that's about the time frame that a lot of the information on smallmouth bass was collected at these sites. So it's not technically present day, but it's the time when growth rates and diets were collected on smallmouth bass. So we did use a bioenergetics model, and the parameters, the physiological parameters from this model came from a paper that Greg Whitledge did, and this actually is from the Ozark population, which is one of our study sites. So that was kind of an advantage that we're actually using some of the physiological parameters directly from the Missouri study site. What we really wanted for this particular project was we needed diets from the fish, and ideally seasonal diets, energy densities of prey, basically how many calories per gram of energy is in a particular prey item, and then growth rates of the smallmouth bass. We actually had most of this information from literature, agency reports, and peer-reviewed publications, and then some of it was just from just other literature and databases that were available. Just to keep things on a level playing field, we decided that we're just going to model a 300-gram smallmouth bass. So every system had the same start weight. We modeled it for 365 days, which was just a nice round number to say what's the annual growth, annual consumption. We didn't assume reproduction in these particular scenarios, just really for simplicity. So real quickly, some of the inputs from the different regions. You can see here that there's actually, we had 2 seasons of data for diets. And there was actually a fairly substantial difference in diets, particularly from the northern to the southern populations. That fish really dominated the Iowa population, for example, particularly in fall, but crayfish was really a big part of the southern populations, the Missouri and Oklahoma populations, where insects, particularly in spring, were dominant in some of the northern populations like Minnesota and Iowa. So we did have differences in the diets throughout the 2 seasons. And then the growth rates that we have here just shows you as well that it's a fairly substantial difference in growth rates, that the Missouri populations are growing pretty slow. They grow to about 250 millimeters at age 4, where in comparison the Iowa is pretty fast growing at about a little over 300 millimeters. So that's really about a 2-inch difference at age 4, which is pretty substantial for a smallmouth bass. So this kind of sets the stage to say that we can input the stream temperature, projected stream temperature in the future that I just mentioned previously, the diets from these studies on these 4 populations, and then growth rates as well, and feed that into the energetics model. And the first thing I want to talk about with this is just the general differences in the temperatures. And I'm not going to dwell on it a whole lot, but with this, I want you to focus on the left side here, just the text. The white numbers there are just the average deviance in temperature from present day, or that 1995 to 2060. So what this means is that depending on the model, remember we had 3 different models, the models showed that our average temperature even decreased by up to 1 degree or 0.9 degrees in Minnesota, but also other models showed that it increased up to about 1.7 degrees. Iowa, kind of the same thing. So we actually have one situation, one model showing cooler water temperatures. When you get down to Missouri and Oklahoma, all of them show positive increases, 1.5 to 3 degrees C. The peak is just the midsummer temperatures that the models predicted. And what I want to show you here is, particularly in Missouri, but even in Iowa, that we had some of our projected stream temperatures 28 degrees, 27 degrees. Depending on which study you look at, that's getting into a pretty high temperature for smallmouth bass preferences. So really kind of teetering on a thermal preference or a thermal limit that after this 27, 28 C, they may not be real happy in that water temperature anymore. So really the nuts and bolts of this particular portion of the talk is looking at the growth and consumption. So this is actually the change in growth and the change in consumption over this 1-year period that we modeled. You'll see that up in Minnesota and Iowa, we had pretty modest increases in growth, 3 to 4%, but they needed to consume somewhere around 15 to 18% more food to achieve that growth. When you head down south in Missouri and Oklahoma, growth was quite a bit more, 10 to almost 20%, but look at the consumption rates. The consumption rates were 48 to 63% more. So really the take-home message with this is that all these populations do appear to grow in the future scenario, climate warming scenarios, but they're going to need, particularly in the south, they're going to need to eat a heck of a lot more food to even have moderate growth rates. And this is assuming food availability or prey availability does not change. It's a big assumption, but it's something that we just have to deal with right now. But this I think the southern populations in particular cause some concern that they're really eating a lot of food. So maybe that means there could be limited carrying capacity issues depending on food availability in the future. So another way to look at the information I just presented to you, and more just in a general way, is that across all populations, in general, a 1 degree increase in water temperature meant about a 7% increase in growth. But to achieve that growth, they needed about 27% increase in consumption. So once again, you're really a relatively modest warming means, yeah, they may grow a little bit, but they're actually going to be burning through a lot of food to achieve that growth. So that was just a real quick background on some of the smallmouth bass work that we're doing, and this really kind of sums it up, that we really didn't see consistent patterns across latitudes. Probably no great surprise there that the southern populations, or at least in the native range of smallmouth bass, that these fish do seem to be consuming a lot more as they start creeping up towards some maximum thermal temperatures that they would like. And to be honest, the reason why we looked at growth is because it was easy. I mean, growth is a lot easier metric to measure than some of these other things like food web dynamics. We're certainly making the assumption that growth is a surrogate for fish health, that maybe it means other things like does increased growth mean maybe increased fecundity or increased survival or other measures of that could be achieved at the population level to show that maybe it's a more healthy population with faster growth, for example. But also the increased climate warming may allow managers to consider how to maybe tweak their management regulations based on maybe harvest regulations, like protecting spawning bass, for example, during the spring, which is something that comes up on occasion. If we have a change in phenology, if we're talking about fish spawning a little earlier or a little later, maybe that start date for a bass season may have to change. Also, just growth rates, particularly in the south, would really increase quite a bit. So if you're protecting to a certain size range, maybe those fish will be 1 year, maybe they're not age 4, they're age 3 by the time they reach a harvestable size. As I mentioned before, I think, though, one thing that we got to keep in mind is that we'd love to figure out how this links into food web dynamics. We are assuming that there is the same food available in the year 2060 as there is now. Not sure that's really going to be the case, but that's really, I think, a next step in this is try to kind of get a handle on, say, for example, crayfish abundance in these particular streams and how those will change with climate change. So just that was a quick overview of our smallmouth bass work. I think, Ashley, we talked about maybe just a little bit of time here for questions about these individual projects, but we will have a larger chunk of time at the end for overall questions. So if we want to, if anyone wants to ask any questions specific to the smallmouth bass work, we can answer them now, or we can wait till the end. Okay, well, so that just ends our smallmouth bass portion of the talk, and that really demonstrated that we do see these potential individual effects of climate change. But now we're going to take it up to more the distributional level and head out east to the eastern brook trout, where Tyrell is going to talk more specifically about distributions in eastern brook trout related to particularly the stream temperatures in that system. So with that, we'll switch it over to Tyrell for about the next 15 minutes or so, and he'll talk about brook trout.
All right, thank you, Craig, and thank you everyone for listening to our talk. So, today I'm going to talk about linking climate and land use projections to stream temperature and then implications for brook trout in the eastern U.S., as was mentioned. So just to start off, for folks, I'm sure all of us are familiar with brook trout. You know, in the eastern U.S., throughout its native range, it's a culturally important species and considered a sentinel of pristine streams and rivers. And so there's a lot of focus on conservation of brook trout and culturally important and considered a game fish of importance throughout the region. So the habitat requirements are pretty stringent in, among fish, and water temperatures typically cold water temperatures less than 22, around that ballpark, considered suitable. They require clean water and clean gravel substrate for spawning, and also suitable flows for egg and larval development. And today I'm just going to focus on the water temperature. So I'll talk a little bit about temperature modeling and then get to brook trout. So as we know, or anyone familiar with the Eastern Brook Trout Joint Venture Assessment, there's less than 30% of subwatersheds have greater than 50% of original intact. So, but what about 80 years from now? Will climate and land use changes cause decline? So declines in populations and where they're found. So the basic outline of today's talk is air temperature and landscape attributes affect water temperature, and these in turn affect brook trout. So the goal of this work is to develop a predictive water temperature model and then to link this to brook trout. And I do realize that landscape predictors can also be shown to directly be related to trout distribution. I'm not going to talk about that today. And then we're going to begin the climate and land use changes. So climate change is expected to increase air temperatures, and land use change results in landscape changes. And then this takes place throughout time, so from present day into the future. So just to briefly go over the temperature model. So the goal is to characterize thermal habitat throughout the region. So we chose to predict mean daily water temperature for all stream reaches in the region. And this is the NHD Plus data set. And we focused on those that are topologically correct, so there's some that are removed, but for the most part, this is it's around 190,000 stream reaches, so it's a pretty big effort. And then chose to use neural networks because they're able to handle nonlinear interactions, and we don't have to know exactly all the processes and the effects of each predictor on water temperature. And then we wanted to assess predictive accuracy and get a good handle of, well, how is this actually going to perform at new sites throughout the region? So even non-random site-based crowd-validation. I won't go into that anymore, but the idea is just to ensure that our calculated root mean squared error is actually representative of if we were to predict at a new temperature site or at a new stream reach. So here's just an overview briefly of the temperature data that I was able to collect. You can see that there's a pretty good latitudinal gradient, lots of data in Maine and Maryland and also Connecticut, and some down in Georgia and such. There are big holes, but I'm very thankful if anyone's on this call who gave me data, and allowed me to use it, I was able to collect quite a bit. We have 1,059 sites after we screened them for effects of dams and problems with some of the records. And these range from 1980 to 2010. So just to go over, I'm not going to read off these landscape predictors, but we did select a range of landscape predictors, both at the network catchment and landscape or local catchment scale, that we expected to be related to water temperature in some way. And then we also had empirical climate data from the National Climatic Data Center sites that read air temperature 1980 to 2010. And at these sites, we calculated both current and a 7-day prior air temperature and used these in the models. So just to look at some of the results of the temperature modeling, what we found was ended up getting what I would say is a pretty good fit for the model. And I should say this is also the period we're modeling between May and October. So it's mostly the warm season, and not dealing with the winter when we have ice and different issues with the rivers. And most of the water temperature data is collected in that period. So the training root mean squared error was 1.98 and the validation was 1.81. But it's a pretty good fit. It follows a linear trend for the most part, but there is some over prediction of low temperatures and under prediction of high temperatures, as you can see by looking up in this area. It's under predicted a little, and down here it's over predicting. But we feel like this is a pretty good model for predicting water temperatures. So then, the water temperature model, we're going to link it, and Craig talked about this climate change data. And the way I'm linking this to the temperature model is to attribute it to these empirical climate sites. So wherever one of these climate sites is found, it's given the air temperature above it from the climate model. And then I'm using the delta method to attribute the changes. So if, for example, the GenMom model predicts a 2-degree Celsius increase between now and 2087, then we would add 2 degrees to the empirical data. And that's a pretty standard way to do a climate change assessment. And then there's also the land use change data, and I just wanted to show this for the region. In our case, there was a lot of agricultural build out in the rest of the U.S., but in the eastern brook trout native range, as I think kind of expected, there's not a lot of agricultural build out, but there is quite a bit of urban development, especially there's huge population centers in New York and DC and Pittsburgh and other places that are going out, and also places in Maine. So there is a lot of developed land use, and this can have definite effects on water temperature and on brooks. And then just to show, I'm not going to focus on the predicted temperature increases themselves today because we want to talk about fish and brook trout populations, but here is predicted water temperature, mean July water temperature in 1997, and here's just an example. There's different temperature classes there on the left side, and then in 2087, using the GenMon model, this is the type of increases that we see, and this is the highest end, around 3 or 4 degrees Celsius temperature increases, depending on where you are in the region. So then, how will we link this to brook trout? We defined suitable temperatures as being any temperature, mean July temperature less than 21 degrees Celsius. We consider that to be a suitable thermal temperature or suitable thermal stream habitat for brook trout. So this was, we identified this using trout occurrence, and we lined it up with predicted mean July temperatures, and it includes about 98% of all the sites where we found brook trout. So we think it's a pretty good cutoff. There's certainly other options, but it seems to be pretty good. And this is what we end up with if we predict brook trout suitability based on that. So that's our starting map. You'll see that there in a few seconds. So I'm just jump now straight into the results. So plugging in the climate change data alone, we have. So this is not including land use change. This will just be climate change alone and holding land use as it is now. Here it is for the GenMom model, and this is the lower end. The projected air temperature increases are quite a bit lower. And in 1997, there's that map again, and then in 2042, around a 6% loss, and you can see that mostly around these edges here, these lower elevation areas around the kind of the margins of the range, and in Pennsylvania where the elevations are a little lower. And then in 2087, around a 23% loss. And again, it's mostly around the victims. You do start to see some in this area, in Vermont area, so, and also up in Maine. And then for the next model, I'm just going to talk about the GenMom and the ECM5. So this is the higher end scenario in ours, and then we had one other model, the GFDL, and I'm not going to present it because it's intermediate, so you can just imagine that it's in between these two. What we see is by 2042, around 10% habitat is lost, and then by 2087, it's around 50%. So this model really predicts big temperature changes around the second half of the century. So, and this is quite a lot of habitat loss, as you can imagine. It's significant, and the areas that you still have left are the really high elevation areas, the plateau in northern Pennsylvania, and down here along in the Smoky Mountain areas. Obviously, we don't have Rocky Mountains out here. So, all right, and then the land use change. I'm not going to show maps for that because it's very localized, and the effects were around 9% habitat loss. So it's hard to see on a map. It's really impossible unless you zoom in on a specific area. So, but what I will show is the additive versus kind of the combined. So I did the two scenarios with climate change separately and land use change separately. And if you add those together, you see over here on the left, I'll focus on the ECM5 for 2087. You get a combined predicted loss of 50.8%. But if you put those both climate and land use change in the temperature model at once and predict future losses, you get around 52% loss. So there are some additional streams that are being lost, and this suggests that there is some synergism between climate and land use effects, which everyone expects, and it suggests around 1.2 to 1.4% additional streams lost that wouldn't lost either one lifting alone. So just to go over what I talked about, the temperature model is, it's kind of, I would say, in advance. It covers a large region with reasonable accuracy, and it can be used for a lot of other studies, such as freshwater mussel conservation and other species of concern throughout the region. And then also the expected effects on brook trout from climate and land use changes, especially climate change stuff. There's been other studies done in the past. Some of the first by Meisner was one of the first climate change studies for all species, and we predicted kind of similar effects of 50%, 23 to 50% predicted losses in brook trout habitat, depending on what the temperature changes were. But this work is linked to individual stream reaches, so it's quite in advance. We can see where they're actually going to be lost rather than using an elevation or an air temperature gradient as was done in the past. But the caveat is that not all of these affected areas that I showed here currently have out. Some of them, one of them actually brook trout found there anymore. So that needs to be in mind. So, and another assumption of the data is, assumption of these results is that there's no adaptation and no refugia. So the brook trout aren't able to find ways to escape these water temperature changes, or to find cold water refugia where they can hang out, which we know they do, and they are able to find this sometimes. And also, how should we interpret these results? It leaves one wondering. I think they should be combined with additional information. So they probably shouldn't be taken on their own to mean that a given stream is going to be lost, because there's a lot in this broad coarse scale modeling that I don't know. I'm not the manager on the ground. But if one takes this information and looks at the stream and it seems like a reasonable assumption, there's not a lot of maybe groundwater importance isn't so great in that stream, and it seems like it could warm by that much, then I think it could be used to prioritize conservation efforts. But the additional information is key. And it can also be used to maintain flexibility. And by that I mean, for example, in Pennsylvania we have cloudy trout streams, and these are certain days, and they get special protection. And if those are lost, if the brook trout populations fall below a certain density or such, that has implications for future water quality problems and conservation efforts, because they will no longer receive the same level of protection unless something has changed. So in the current system. And then a future effort that I'm focusing on is the role of riparian forests. So in the temperature model, it does include a riparian forest scenario, riparian forest as a predictor. So I'm just looking at that and looking at different scenarios to see how that might affect water temperatures in light of climate and land use change. So conclusions: brook trout could lose up to 50% of thermally suitable habitat due to climate change, and it acts broadly across the whole region, whereas land change acts locally. So, and it's minimal habitat losses from land use change, but a lot of these streams are on the edges of cities, or maybe they're really culturally important streams because they're near population centers where many people are fishing. And there's also related fisheries and water quality implications from this land use change in primarily developed land and urbanization. And these projected changes can certainly help guide future decisions, especially when combined with additional information. So with that, take any burning questions if we have them. We'll also take some at the end, but if there's any that are out there from now.
So we do have a question from Monty Schmidt. It says, could this modeling effort inform or even map where stream restoration could mitigate long-term climate change impacts?
It can, depending on what the stream restoration efforts are, because the limitations are broad core scale predictors such as land use throughout a local catchment, or also riparian forest, which is just defined by the national land cover data set at 30 meters on each side of a stream. And my preliminary results that I had before, it was a little different temperature model, but it's pretty similar. They suggested that the climate change impacts were around 10% less in some cases, especially for the higher end temperature increases. So there was a significant effect of riparian forest on maintaining stream habitat. I don't know if that answers the question, but I think that's probably the limit. Yeah.
Did you want to? Do you have anything else?
Nope. I think
okay.
That's.
All right. We have another question from Thon Hit, and it says, "Can you talk more about how air temperatures influence the stream temperature projections? For example, did the Delta model assume a 1-to-1 relation between air and stream temps?"
Oh, okay. I'm sorry. For that, we did not assume any relationship between air temperatures and stream temperatures and how they're related. The neural network model was basically used to do that, but I could say based on I did some diagnostic plots, and it's very similar to the Mosini plot. If you've seen this, probably depends on which stream you're in, but around a 0.8 degree, I would say, increase in stream temperature per every 1 degree increase in air temperature. But you also see that flatten out as you get warmer. But we let the model kind of decide what that relationship was. The Delta method, on the other hand, was just for the air temperatures. So I was hoping that wouldn't confuse anyone. But basically, for the Delta method, you have a given climate site, and because there's the empirical climate data and the model climate data don't overlap, one may say that in May 24th, 2013, that it's, the empirical data says it's 26 degrees, and of course the model data says it's, maybe it says it's 22. Well, that's not what we're really interested in. We're interested in what did the model say that temperature will increase. So you just add the expected increase to the empirical data and kind of ignore what the model said the temperature was at your baseline. So if it says in the future it's going to be 29 degrees and now it's 26, then you would add 3 degrees increase.
Okay, thank you. We'll take one more question, and then we'll hold the others till the end. This one's from Ann Tim. It says, what is the main difference between the ECH AM5 model to the other models?
I'm going to have to divert this question. Yeah, it's not something. It's probably a more of a climate modeler's question. I call it ECM 5, and I mean I know that it predicts higher temperatures in the end, but the scenarios are all the same. I can say that the scenario as far as how much carbon is going in the atmosphere is similar between all models. So it's what are the forcing factors.
Okay, thank you. All right, we're going to switch it back over to Jody, and then we'll take the other two questions at the end.
All right, thank you.
Thank you. Thank you very much, Tyrell.
Okay, this is Craig, and I'm just going to provide a brief transition. But basically, you know, we've seen now so far that at the popular or individual level, smallmouth climate change may affect smallmouth bass. We've also seen at the distribution level how it'll affect brook trout. Now we're going to do something completely different and head on over to the desert Southwest and talk about fish communities, particularly native fish communities. And I think in the next few minutes you'll realize why we went out here, that we're going to see some pretty drastic differences and challenges related to water in the Southwest.
Okay, to give a little bit of background on this area, as Craig mentioned, we did select this area because it is topographically, environmentally, and climatic-wise quite different from our other regions in this project. So we were curious to see what we might be able to do in terms of changes in stream habitat and the fishes that live there. Our primary objective was looking at the potential changes in stream habitat based on shifts in land use and climate. We were looking to identify streams and watersheds that would be vulnerable to those changes. As many of you know, the lower Colorado River Basin is primarily a desert system, so very xeric with very low rainfall. There are also a very high number of endemic fish species, and unfortunately, an even higher number of fish species that have been introduced. At this point, there are estimates of nearly 90 species have been introduced, and of those, about 2/3 have actually become established. It's also a region that has incredibly high urban growth rates in the Vegas and Phoenix areas, which of course then leads to additional demands for water. Water is being used for urban uses as well as a high proportion of agriculture. Our initial approach was, for the regional projects, we were going to try to predict potential changes to stream habitat conditions by developing stream temperature and flow models. From there, we would hoping to use that to project the shifts in habitat conditions, as I mentioned, from land use and climate change. And then we were hoping to be able to link that to, in our case, fish communities, and in some of the other regional projects, they were going to look at individual species, such as what Tyrell did. And we were also thinking we might be able to use the fish traits to tie into those changes. Unfortunately for the lower Colorado, we had to change our plans on that. When we started exploring the data sets that were available, we contacted federal and state agencies, universities, NGOs, and other groups and individuals, but we just did not find enough data to develop year-round temperature models or flow models. In this figure, this just shows you where we found some continuous stream temperature data sets, but then when we filtered for trying to get year-round data, it really limited what was available and the total distribution of those. We did explore trying to use the method for the national assessment, which will be discussed in detail next month, with our thought being that the additional fish data that we had might help us refine their method for the lower Colorado. Unfortunately, we also ran into another roadblock here because very few number of sites met the requirements that were needed to conduct the method based on the national assessment. So once we determined that the methods proposed for both the regional scale and national scale were not going to be possible or did not add much additional insight for the lower Colorado, we took in different tactics. Previously, we had developed species distribution models for fishes in the lower Colorado that included proportion of ag and urban land use and also variation in spring and winter precip and average annual temperature. The details of that method can be found in Strecker et al. 2012 Ecological Applications. One modification we made to this method is that initially, or previously, we had conducted community models but in this case, we wanted to detect the differences in how species were responding to climate and land use, so we ran individual models. These initial models had been developed using 30-year climate data, so that's what's indicated here is we used a current, a 2040, and 2085 time steps. This figure here shows the temporal coverage of the downscale climate models our group used. Just briefly, we ended up for the lower Colorado using the ETM5 and the GenMom, which is Tyrell indicated earlier. This was a high change and low change, with GFDL being the moderate. And as you can see, we didn't have enough temporal coverage for this model to be able to conduct these 3 time steps. Today I'm just going to be talking about the more conservative model of the GenMom. This is a list of the species that we were able to model. Because we ended up shifting to the individual models, our numbers of species that we modeled dropped slightly, and we ended up with 16 native. As you'll notice from this table, a lot of these are endemic to the lower Colorado, and only one is found elsewhere outside the Colorado system. I've highlighted the humpback, pike minnow, loach minnow, and razorback just to point out the sample size, which I think will come into play as I discuss some further slides. All modeled species had significant response for at least 2 of the climate or land use metrics that we were varying in our future models. All species except for the razorback showed a significant response to urban land use. The next most influential variables were variation in spring precip and average annual temperature. Now this figure shows the directional change in distribution based on the difference in the number of stream segments that qualified as occupied using the conservative threshold of a 0.6 probability. Between the current condition and the 2085 time step, 7 species increased their distribution by more than 25%, and 4 of those by more than 100%. However, keep in mind, percentages can be a bit deceiving. The distribution of pike minnow appears to skyrocket, but this was really only a shift from about 10 stream segments to 100 and was restricted to primarily the Verde and Salt River system. So as I indicated previously, there can be other factors going on that we were not able to capture in our species distribution models. At the other end of the spectrum, it looks like 5 species have decreased by about 25%, and 3 of these are endangered and 1 is threatened. I want to highlight a couple of these species just to discuss the strengths and caveats of our results and how managers might apply this information. So with the humpback chub, this species is really restricted to the Colorado main stem and the lower end of the Little Colorado. So although it appears that it is decreasing by about 50% of its range, one thing to keep in mind is the scale of the data that went into these landscape models and how species with these very restricted distributions, we may not be capturing enough of the climatic influence because these climate models are at such a coarse scale. Where it appears the humpback seems to be losing habitat, this actually is not terribly good habitat for this species in the first place. So this shift from a current existing in 33 stream segments in the Little Colorado down to 16 stream segments may seem like a lot, but in reality, the scale of this information may be causing some problems. However, on the other side, with the distribution of the loach minnow, this already occurs across several watersheds and in different systems. At this point, the current restriction on this species range shows it existing below 2,200 meters, but with these projections, we actually see it moving up in elevation to about 3,000. So this could be actually a real response to changes in climate as well as land use. How does this fit in with we wanted to see how this fit in with the Desert Fish Habitat Partnership rankings, thinking that, see how well the response to climate might be already captured in this. And unfortunately, it doesn't look like there is a strong correlation, but keep in mind that one of the components they incorporated was the level of management available. So some of these species with low rankings swayed what might have been a correlation. So for the Colorado River Basin, we had hoped to be able to follow the protocol that our group developed for the regional assessments. However, due to data limitations, we had to explore alternative approaches. We first evaluated whether we could refine the results produced using the national approach, given that we had access to additional stream temperature and fish records, but found that we were still data limited. Ultimately, we used a coarser approach than the other regional projects where we incorporated downscaled climate metrics for air temperature and precipitation to model changes in species distribution as a surrogate for changes in habitat condition. Based on our models, there does not appear to be any correlation between the Desert Fish Habitat Partnership rank and our projected changes in habitat conditions or distributions. I know they've been discussing possibilities of trying to incorporate some climate metrics into their projections, and so this may be further justification for trying to build some of the influences of climate and land use change into their rank levels. Now, one caveat to keep in mind on the way we approach this was that we're assuming that percent occurrence by stream segment is actually reflecting changes in the habitat suitability for these fishes, and that the air temperature, precip, and land use influences are somehow linked together with other environmental factors to actual changes in habitat conditions. We do believe that the extreme changes are likely more informative than those slight, subtle changes, either on the positive or negative side. However, we really did also find that species with very restricted distributions are much more challenging to address because of the landscape scale and coarse scale of a lot of the data sets that we have available. We do feel that the information from these models can be used in more large picture management plans, more large scale management plans, as well as also looking at potential future directions for research, in particular trying to get to the mechanisms that could be driving these shifts in habitat conditions. With that, I'm going to turn this back over to Craig.
Well, and I'm just going to quickly wrap up a few slides here, but really over the last hour or so, what we wanted to demonstrate on this project is that what we have learned is that the individual and population levels, such as smallmouth bass in the Midwest, that they may need to actually eat or consume quite a bit more food, up to 27% more food, for a relatively moderate increase in growth rate of about 7%. Now, if we go to the Northeast and talk about brook trout distributions in the Northeast, based on some of the climate projections and the work that Tyrell has been doing, that brook trout could lose up to 50% of their suitable thermal habitat. And then if we go to a completely different basin in the lower Colorado River, where it's a very arid system, that we actually found that several warm water native fishes would increase by even over 100% or double, where a couple of them would actually decline. But one of the challenges here is we have many species with restricted distributions. They're in a relatively small area where they live. For example, the humpback chub is only found within the Grand Canyon reach of the Colorado River and some of its lower tributaries. So using these downscale climate models and these broad-scale analyses to address some of these issues of distribution for a relatively restricted species may be challenging. So that's where, as Jody mentioned, going to the larger spatial scale, larger analysis, big picture, is probably more appropriate given the uncertainty on these climate models, and we're taking a global model and downscaling it to a local level. Now, one thing that I want you to keep in mind is when we started this project, particularly these regional projects like eastern brook trout in the lower Colorado River Basin and what you'll see in the upper Midwest next month, the idea was to try to keep these methods as similar as possible because that was the whole idea, is to try to keep these consistent. We couldn't, and Jody just mentioned it, one of the reasons why we can't. In the lower Colorado River Basin, when you're talking about just very few sites, relatively speaking, with stream temperature and flow, and particularly as you link those up to the ones that had fish, it became less than 8% of the sites. The brook trout data that Tyrell was talking about actually had quite a few sites. I mean, over 1,000 sites with temperature. What you'll see in the upper Midwest, which is Michigan, Minnesota, and Wisconsin next month, is that we're going to be looking at, there's about 1,700 sites. And when you just take a simple calculation of the percentage of actual stream reaches in the region that had temperature, the lower Colorado River Basin had just 0.2% of those, and that's actually rounding up. I was trying to be conservative. Even though the upper Midwest is only a little over 1%, it's still substantially more than the desert Southwest and even the eastern brook trout. And for folks that have been linked up to the fish habitat partnerships, this is no great surprise. One of the big issues with trying to get at some of the data we need is we need more stream gauges out there. We need more flow information, need more temperature information. So this is no great surprise on that end. So as I mentioned, that really the approach that we took was dictated by the data, and the desert Southwest was a good example of that. We would have much rather tried to link stream temperatures and flows to fish. We just couldn't, given the data we had. But in the eastern brook trout range, they could. So we're really hoping to provide a framework and recommendations that, given the data you have, what can you do with this information? So trying to kind of put a positive slant on it, other than everything's doom and gloom. Given the information, what can we do? And so next month, you'll see the next half of this webinar, and that's actually going to expand out that we're going to focus mainly on the Midwest from a lake component in the cold water lakes in the upper Midwest, as well as Midwestern streams. And then we'll also talk about doing this very coarse scale national assessment as well. So you just kind of got a taste of the half of this project, and the other half will be coming May 9th. And I believe that's really it. Obviously you can imagine we had a lot of help on these projects, particularly with the existing data and leveraging existing funds from NIFHAP, from Aquatic Gap, and then some folks that I mentioned before, and the Climate Change Wildlife Science Center and USGS funded the work. And then from the individual projects, we listed a lot of people here that offered data from the Brook Trout and the Lower Colorado River basin as well. And so at that point, I think that's it. And I guess we can open it up to questions specifically to the Lower Colorado River or just in general across the whole talk.
We do have a general question about the funding. Geneva Johnson asked, is there funding to help get more stream temperature data for the Southwest? I know managers who are willing to pay for the temperature gauges, but can't fund the data collection.
Not coming to us, at least. I know that's been talked about. I'm not sure if there's anything ongoing efforts with that, but if there are, it'd be great. But as far as I know, there's not, at least not directly related to this project.
Stephanie Coleman mentioned that she's got. Stephanie, I don't know if you're still on the line. It says you've got some funding for data collection.
Hi, this is Stephanie Coleman. What we're doing currently, I work for Forest Service on the Apache Sitgraves National Forest, and right now I'm using just Forest Service general program funding to fund data collection. Now at this point, it's only enough for a few loggers, but I'm trying to press, at least through the region, that this should become part of our just general management. I don't know how far I'll get, but I'm also interested in other avenues for acquiring funding for data collection.
I can say that at least this is Craig again, but at least in the state of Missouri, so not the desert Southwest, but we actually have a state-funded project to develop stream temperature and flow models throughout the state, and we're throwing out, Jody, what is it, about 80 sites right now throughout the state, and putting them in there, putting loggers in there for at least 3 years. But that's the Missouri Department of Conservation funding that work, so no federal funding. And
Park Service has also agreed to help do another about 12 sites.
Jody, I think you answered this somewhat. And Stephanie also writes that the Apache Sitgraves National Forest is working towards getting a stream temp monitoring network set up on the forest. How many years of the stream temp data are needed to run the models? And can the models be used at a smaller forest scale? Did you guys cover that just now?
I would say we should try for at least a full continuous summer to make a first stab at it. Preferably if it could be multiple years and year-round, particularly out where you guys are, because you're kind of in a similar situation that we are here, where the changes in the winter might be, particularly in the lower elevation areas, might be really important too, as we see the winter temperatures start to increase, and how that might influence how the aquatic communities are going to respond. The more continuous data we can get, the better chances are we can do some models, get some robust models off of those. We found, and just from looking at literature, that it doesn't have to be, you don't need to be doing like 15-minute records in order to keep the temperature loggers out there longer and lasting. Hourly it seems to work pretty good, if that kind of gets to your question. You know, more data that we have, the better. But there's also a trade-off of funds and time.
You know, one issue that when we brainstormed about this with Steve Hostetler, that obviously makes a lot of sense intuitively, that it depends on the year too. I mean, that if you have a really high water year or a really low water year, you know, flows may really affect temperature as well. So getting, say, one continuous year or a summer of stream temperature data is useful, but only if that's truly representative of what's, you know, happening over a broader time scale. And certainly as you look in the, you know, northern climates, the focus is just more the summer maximum temperature. They're not caring a whole lot about, you know, what's going on in January.
In regards to the funding again, Geneva Johnson had written possible landscape conservation cooperative funding as a source as well. So.
and probably the folks that are listening, when we talk about stream temperature modeling, most people are probably aware of Dan Isaac out of the Forest Service in Boise, and he's got a blog and all sorts of temperature data, and he's kind of the go-to guy, I think, now when it comes to stream temperature and fish relationships, and other folks around the country are also leaning on him to try to integrate stream temperature data, throughout at least the northeastern U.S. and link it also to the western U.S. where he's at.
And if anybody's interested, we do have a webinar that is archived of Dan's. You can send me an email and I will send you the link. We have a question from Doug Beard, Director of the National Climate Change and Wildlife Science Center. Doug?
So, Craig, and I apologize, I've got laryngitis, but it's getting better. And I'm going to ask you the question Dr. Carter was so afraid to ask. You had a nice description of how these projects link together, but I guess could you kind of expound on some of the challenges of trying to do this sort of multi-scale analysis and some of the things that we could learn from what you found and could apply to other approaches, because that really is the holy grail, trying to figure out how to put together projects that fit questions at multiple scales.
Yeah, so probably the first thing that I can think of offhand goes back to the downscale climate modeling, and this project was funded, I believe, in 2009, if I remember right, and there's a lot of downscale models going on at that point, and a lot of concurrent modeling going on. So we would hear about other models, other modeling efforts that were going on, and really didn't know a whole lot about them. So I think one thing that I think would be useful is just getting more communication around the U.S. about what actual climate models are being done and the pros and cons of those, and particularly being, fish folks like most of us are in this group, that we're relying on, our climate modeler, Steve Hostetler, to kind of tell us what works and what doesn't. And unfortunately, these things just take a heck of a lot of time to process. So that was a challenge too, is that we would be waiting for an additional model to finish before we could continue. But knowing just what scales different models are using, maybe there's some modeling being done at another region that means that we don't have to do any modeling, say, for our particular project. So I think that would be one advantage, is just trying to kind of put all the modeling pieces together. I think probably the second one is just the data availability is probably the biggest issue that we saw, and you can see that in the Colorado River Basin. And unfortunately, it's just something that we keep harping on, and most of us don't have a whole lot of control about getting more gauges out there. But the idea would be that we're trying to do with this project is, try to create a threshold. I mean, at what level of data can we actually say something, and at what level, how much data do we need to actually make some sort of meaningful analysis? And you're going to see from the upper Midwest and Tyrell's work, where there's thousands of data points out there for temperature. That's really useful. Now, there's the gradient in the lower Colorado River where it's not useful because we have so few. But somewhere, there's got to be a happy medium somewhere in between, that we create a threshold where we have enough data to actually make some meaningful analyses. Hopefully that's a start of answering your question.
Yeah, thanks, Craig. That does some more illustrate some of the good challenges, but clearly one of the things we ought to think about doing when you guys are done and after the next one is have sort of I don't know what you call it, but a deconstruction or a lessons learned sort of thing, so it can help us when we try to do another one of these projects of these scale.
Yeah, I think that's a great idea. I think a lessons learned is, there's a lot of them, and one of the reasons why we chose these different regions of the country is because we figured we'd have different lessons based on the different regions, and that's exactly what happened.
Thanks, Craig. We have another text chat question from Sally Valdez. Any assessments on climate effects on fish in coastal and/or marine environments?
Not on this project. I suspect there are some going on, but not specifically for this project. We actually talked about it because one of our bases was really NIP, the National Fish Habitat Action Partnership, but just because of the the limitations that we had as far as this was as big a project as we wanted to handle, just looking at actually interior systems. And in fact, to kind of take that a step further, we had just one lake project, a natural lake project that you'll hear about next week in the upper Midwest. So another one that we've been ignoring is really lakes in other parts of the U.S. and reservoirs as well. So this is 80% stream based, and so not only are we missing coastal environments, but we're missing kind of the reservoirs and lakes outside the upper Midwest.
Thank you. And then there's some great conversation going on between Stephanie and Leslie. And then also Yingvan posted, for those interested in the temperature data, Northeast Climate Science Center founded a stream temperature inventory mapper and data portal. The mapper and portal is in progress. Thank you very much.
And you'll hear more from Infan next month because she's part of this project looking at the national assessment.
Excellent. And then I did just want to point out that Terrell did answer Jennifer's and Dan's questions to his presentation. So if you guys can just take a look at that in the chat box, and if you need any clarification, please just let us know. While we're waiting, Craig, do you have any closing remarks?
No, other than, thanks for everyone participating. It looked like we were somewhere up in the 70s range, so glad to see that, and glad to see, some NIFHAP faces or names on there, and some folks from throughout, I think, all regions of the country. So we appreciate the interest.
And definitely anyone who wants to, feel free to contact us directly if you have any other questions or any other thoughts down the road.
I have the beginning slide up, and down towards the bottom at the center is our website.
All right. Excellent. Thank you very much. Holly, do you have any closing remarks at all?
No, I don't think so. Just thank you so much. That was educational and excellent. Thank you.
Glad to do
it. I'd like to thank all our presenters again. Very, very good presentation. Thank you. And thank you to all our participants. I hope that you enjoyed it.